Okay, so before we move into Chapter 9, let's just do a quick review of some of the concepts from Chapter 8. So frequency, wavelength, wave speed, medium, graph shape, those are ideas we looked at in Chapter 8. And this is a PhET simulation. These are awesome to explore and play around with. So if you click on this link in the PDF, you should be taken to this website. And I have this linked up to the waves intro. So if we look at something like water, just make sure this picture fits inside our recording area. You can turn on the tap here and you can see waves being generated. Dark are troughs and light are crests. There are some tools on the side where you can measure. You can have a timer. You can do a bunch of things like this where it'll show you what's happening with the graphs in terms of the water level. You can play with the frequency, so you can slow down the frequency. You'll notice, okay, this frequency has changed. If we speed up the frequency, okay, the water drops fall a little faster and you start to see rings coming out in a tighter package. Okay, you can change the amplitude and those types of things. I'm just going to do a quick, slow this down just a little bit. If we turn on the graph, this is one of the pieces we want to look at, and maybe we'll turn the amplitude up. Okay, so you'll notice if you look at the graph, it's showing this line right here. Okay, and wherever you have a light line right here, that is a crest. Okay, so wherever you have a dark line, if you follow that dark line down, that is a trough. Okay, and amplitude is sometimes connected to energy. It's just a rough connection, so you can see there's a bigger amplitude here, but as the waves move out, they do tend to lose a little bit of that amplitude as they spread out, and they start to be a little bit more consistent further away. You can look at side view, so you can see the water dropping up and down. So these are kind of fun little ways to explore waves without having to fill your kitchen sink. Okay, and they have other ones. We have something like sound. So when we run sound here, sound comes out in waves. Now remember, these are rarefactions and compressions. These are different than transverse waves. So you can actually see the particles if you turn them on. So what you will see is that net displacement for these particles, they move out and they move back. They move out and they move back. So you can put on both of these and you can see how those little particles are just moving back and forth. So they're dense for the compressions and they're spread out or less dense for the rarefactions. Okay, and then lastly, if you want to play around with it, you can take a look at what light looks like. And light will spend more time within grade 12. But you can see over here, instead of giving you frequency numbers, they actually give you the visible spectrum. So if you shift this to red, you'll notice that the frequency, okay, a little more spaced out, a little less, not quite as densely packed rings coming out of that light. If we crank that up to ultraviolet or near the violet range, you'll see it's a little tight, more densely packed. Okay, and those are just things you can play with at these PhET simulations. So something to spend some time on. Those links are all on the website. Okay, so now let's get into wave interference. So by the end of today, I'll be more familiar with the interaction of two independent waves. Okay, so waves are the result of particle vibrations, and that the particles in a medium are connected by forces that behave like little springs. So wave motion is efficient. In most media, little energy is lost as wave moves. So when waves come together, this efficiency continues. So we have a picture over here. We have a wave traveling to the right. Okay, and we've modeled it with a little circle because water particles, if you're in water, they do move up and down, but they also tend to move a little bit forward and backwards. So what we want to see here is what happens if two waves, one coming from the left and one coming from the right, collide. Well, you can see there's a little wave here of a certain amplitude, and then when they collide, we get this really big wave. Okay, and one of the pieces to take away from this, okay, is that none of the characteristics of the individual waves change. So that is this piece. Let's just get a highlighter out here, right here. So wavelength, frequency, amplitude, none of that changes. Okay, so the two waves essentially collide, affect each other, and then just keep on moving as if they never met. Okay, so we have something called constructive and destructive interference. They're both going to fall under this concept that we call superposition. So at any point, the amplitude of two interfering waves is the sum of the amplitudes of the individual waves. So we're going to add up amplitudes is what we're going to be doing. For constructive interference, okay, they'll generally form a larger wave, and for destructive interference, they'll sometimes cancel each other out or make a smaller wave. So if we have a picture that looks something like this, you can see that this is coming in as a +1, this is coming in as a +2. The two waves collide, and this is sort of showing you step by step. When their peaks or their crests are aligned, you end up with a +3. And then as the waves continue, they fold out from each other, and then they carry on their way back to being a +2 and a +1, and they carry on their separate directions. Okay, so destructive interference, okay, you have a +2 and a -1, or a -1 here. So +2 and a -1. So when the crests here, or crests and troughs, collide and they get to right where they're in alignment, you'll notice that it drops down to being just a 1. Okay, so that's destructive interference. This wave here on the bottom is actually dragged down or lowered the amplitude of the top wave. Once they pass through each other, they carry on and they're right back to the way they were. Okay, so if you want to pause it here for a second, take a look. You can read this through. This is in your textbook. And it's just giving you some different shapes. So not everything has to be a perfect curvy wave. Some can be little boxes, some can be triangles. Electronics, you have a lot of different shapes. So just pause that and have a look. Okay, so if you had a chance to look at it, this is where the two waves are aligned completely. Okay, so that front element, the first element, they are both 2 blocks high, so that front element cancels each other out. So we get a resultant over here of 0 at the beginning. Okay, and then if you measure this element at the end, it is +2 on the end, and that's why it finishes as +2. And then the two waves carry on their way. Okay, so something like this, if you want to try and make it practice or a guess here, one thing to note is this is only 2 units wide and the wave on the bottom is 3 units wide. Okay, so if you want to take your sketch, I've made mine over here. So let's see if I can pick it up and move it. Yeah, so, oops, there it goes. So you'll notice if I lay it on top here, it's pretty darn close to following the pattern of that triangle shape on the bottom. And then when they interact, this top part of the square box on top, because it has an amplitude of 2 on the top, let's get that pen out here. So this 2 here in the middle and this 2 here of the triangle, when they're completely overlapped, then they would have result with a 0 in the middle. Okay, and then the other parts we kind of sketch in as best we can. Something similar, if you have two waves, again notice this one is 4 wide and this one is only 2 wide. They have an amplitude of +1. So a quick little sketch, if we're going to have this wave collide when they're right on top of each other, because it's only 2 wide, it'd be something like that, with a little bump or dimple on the top, and it should get an amplitude of 2. Where is this used? Sometimes if you have noise cancelling headphones, these are really cool creations, because inside noise cancelling headphones they have little speakers that pick out the outside sounds, and then microphones on the outside that pick up the outside sounds, and then they have speakers on the inside. And what they do is they create the same sound but out of phase, so that when the two waves interact they cancel each other out. Okay, and that's where the noise is decreased or eliminated, and it allows for a very quiet experience. Okay, so there are a couple more, let's go, PhET simulations out there that are kind of fun to look at. Wave interference, this is another one, and you'll have lots of time to play with these. So here's waves. Okay, so we've already looked at this one quickly. I'm going to go down to wave interference. So if I turn on one wave, or one tap, and I'll show the graph of that. And what I want you to see is look at the amplitude here of that wave. Okay, it's not really going past halfway up that one block. Now when I turn on the second tap, we're going to get an interference of the water waves that it generates. And you'll notice immediately, now that amplitude has changed. It's now going all the way up to 1, where it used to be just going up to a half. These, and it's traveling along this white line. So these really deep or bright blue spots represent the crests. The brighter they are, the higher they are for this particular demonstration. You can see some dark areas around here we'll spend more time in grade 12 talking about. So those black spots are the troughs and the light spots are the crests. So if I turn off that bottom tap again, you should see the amplitude start to drop because nothing's interfering. Okay, so you don't have that combination of constructive and destructive interference making larger waves. Okay, so let's leave with a couple of questions to try. So section 9.1, 1 to 3. And tomorrow's a longer note, so I'll try and keep this one shorter. Thanks for tuning in.